Okay, Assalamu alaikum, good afternoon. It's our pleasure to introduce Engineer Ali Zain, one of our instructors in Spark at Spark for consultation and technical support, who will be delivering a free 2-hour session in the field of process safety and risk management. Engineer Ali has more than 14 years in this field. We are confident this session will be provide a valuable and practical understanding of key process safety principles and risk management. Kindly keep your mic muted. For any question, please write them in the chat box, and our instructor will respond accordingly, inshallah. The floor is yours, Bashman Saad.
Okay, thank you, Dr. Ahmed. Thank you, everybody. Today, inshallah, we are talking about a small defect impact. This is the subject of our seminar. Welcome, everybody. This will be talking about the inside a failure. This is the main subject of our seminar. We will learn how small defects lead to major plant accidents. My name is Ali with you, as Engineer Ahmed said. I'm interested in asset integrity consultation and instructor of with ABI training programs. Inshallah, today we are talking about these outlines. Webinar outlines will be focused on 4 pillars, as we can see in this slide. The first subject that we will discuss, understanding failure evaluation. Specifically, we are talking about the mapping for the defects to be reached out to be a major accident. Then we are talking about identifying risk-prone areas. Mean that's talking about specifically the area or the high risk area in the facilities and high risk area in the each or individual equipment. Then we are going to talk about generally about asset integrity management, focusing on inspection and implementation of international standards and ABI codes and standards. Then we are close our session with some about some notifications about risk-based inspection, or we can say some tips how to calculate risk-based inspection and how can we calculate the risk and identify the high risk area. So this is the first slide that talk about our outlines. Firstly, we should know what does it mean by defects. What does it mean by defect itself? The term defects is a measurable discontinuity material, we can see, or imperfection, local deviation. So any of these mean that this will be named as a defect. So any discontinuity or imperfection or local deviation, whatever the reason or the main cause for this discontinuity or this imperfection or these local deviations, finally this out of acceptance criteria, or we can say it exceeds then the limits of accepted point, so that it became defects. Okay, so let us agree that the defects is considered as a discontinuity or imperfections that comes from the different reasons. It could comes from design conditions, or we can discuss another reason cause the defects. But before going deeply talking in this definition, we should know that the defects doesn't necessarily mean a failure, but we can say it is considered an initiation point of degradation, so that we will focus on the defects. However, it's small defects, and we will explain why defects or small defects never ever is safe. Okay, so when we are talking deeply in engineering interpretation, so we can say that there are some reasons, or we can say some methodologies, we can appearance. Here we can see some cracks from cyclic stresses or hydrogen media or hydrogen surface. We can also say that some defects related to wall thinning, This may be happened or occurred due to corrosion, erosion, or we can see this weld imperfection exceed the acceptance criteria, so it became defects and need action. Here, the last the pitting, or this is another kind or another appearance from the defects. This is from engineering interpretation. So from engineering interpretation, we can say there are some reasons or some appearance, visible appearance for the defects itself. As we can see also, there are some additional engineering interpretation, for example, coating breakdown, exposing base metal. We know that the coating itself is considered as the first barrier for the corrosion mitigation. Okay, so in case of any coating failure or degradation or breakdown, this is considered also as a defect. So defects are a physical evidence of an active damage mechanism. So we are going also to talk about the difference between the damage mechanism and failure mode. Here also definition for some small defects. Small defects means some micro cracks that appeared due to some different reasons, as we discussed in the previous slides. Also some shallow pitting or localized galvanic attack that penetrate wall thickness vertically. Okay, also some inclusions. This inclusion or this impurities, this is trapped from the manufacturing process or may be trapped during repair by welding. Here we can see this is this photo explain the macro defects. Micro defects started as a shallow depth, then became this area as stress risers and stress concentration. In the blue photos, we can see this is the magnification of under microscopic photos explain. However, the appearance from physical by neck or by neck eye is a small defects, but actually it's a huge defect. So firstly, we should know that the small defects may be appeared physically by naked eye, but actually it is has a huge or large depth, and it will be affect the equipment by any way by the time or by operating, exposing to operating parameters and operating conditions. Here, this slide also summarizes what we discussed in the previous slides. There is a huge, we can see micro cracks. Here, some pitting also, we can see at the metal loss. And here also, this is an inclusions or impurities. Okay. For micro cracks, we should know that these micro cracks may be intergranular or transgranular. So what does it mean by transgranular and intergranular? Intergranular mean that the crack direction take the same boundary of the grain size, but for the transgranular mean this cracks is directly perpendicular and deeply and they didn't match it with the grain boundary, but it's deeply and this pass the perpendicularly to the boundary. Here we should know that, as we discussed before, why small defect is never ever safe. It's extremely clear that there's some started by initiation, and then after that propagation. We can see in this in right side this photo, and then after that failure. And this is a chain that discussed and explain why small defects is never safe. Why it's never safe? Because nowadays this is the initiation, and we can say this is in startup of these defects, and we can continue working without any attention. But unfortunately, this after that it became a stress concentration. This concentration means propagation, as we explained here. Then failure could be appeared. This also we can see in this photo. This is the initiation of these defects, and then occurred propagation, and then after that we reach out the accident. So from this slide we can say that small defects couldn't be considered as a safe, and it should be under monitoring and take a necessary action to avoid reaching out the failure phase. Here, this slides have this graph, exponential defect growth with time. We can see here this is a relationship between the time and the horizontal axis. Okay, and this is the defect size, and also we can consider this is the risk. By the time, if we consider nowadays, we are still a small defect, and no action is needed nowadays, but unfortunately, the propagation is still with time until reaching these points and major accident or major incident. So now we define or simple definition for the defects, and now we are going deeply in the process and the operating parameters, specifically talking about integrity operating window. What does it mean by integrity operating window? Integrity operating window, as we can see in the right side here, it's considered as some process parameter. We can say minimum and maximum boundary for the process parameter, for example, for temperature, for example, for pressure, temperature, flow rate, and so on. So all variables or process parameters should working without moving or deviation from this boundary. Unless otherwise, it will reflect on the defects on the equipment itself, or we can say in the structural integrity of the equipment. For example, let us take an example. Okay, if we have a fired heater, and this fired heater, the fire tube inside fired heater supposed to expose to the maximum temperature, for example, 300 Celsius degree. Okay, if the temperature is raised this temperature, so it will be exposed to creep rupture, and moving outside or working outside this window will affect directly, and unfortunately it could happen the major incident. Finally, it could be finished as a fire or a huge fire, depend on. Another example in related to the temperature, suppose if we have a cryogenic media or surface, meaning working in the minus Celsius temperature. If the temperature is below this limit, so that the equipment is exposed to brittle fracture. So finally, what we try to do by operation team restricted with the integrity operating window. Why? In order to avoid exposing the equipment to the defects, and after that this defect be propagated until the failure could be happened, as we explained in the previous slides. We have API recommended practice 584. This talking specifically about integrity operating window and how to establish integrity operating window, and also this guideline or this recommended practice talking in details about integrity operating window, how can generate integrity operating window, the integrity operating window flow chart. It will be found in this recommended practice. So as we explained in the previous slide, let us agree that this rule, moving outside this band or these limits, directly will affect the equipment, and the risk model became clear. Okay, this is for the integrity operating window, and we should talk in details about integrity operating window. Why? Because our session today talking about small defects impact, and we started by the simple definition about what does it mean by defects, and moving how can we found these defects. These defects it came from different resources, as we explained and illustrated in the previous slide, until we reached into the definition of integrity operating window in the oil and the gas. Each client have, or every client have a separate integrity operating window, and from this integrity operating window, the operation team should prepare a procedure or operation procedure to match and to align with the integrity operating window. Finally, to keep the equipment in safely manner and keep and achieving the reliability to the equipment without any stopping or without any interruption. The first thing that we will discuss today, understanding failure evaluation, specifically mapping the path from the defect to the accident. From this chart, we can see that this is early catch and this is late catch. We can see this is the point no return back again, and the failure will be occurred by anyway. So this is the relationship between the time and the degradation. Okay, and we are going to talk about the failure propagation until reaching to the accidents. Okay, as we know that nowadays in the modern industry facilitated, the line between peak performance and total shutdown is too much thinner than ever, so that our assets are constantly under environmental and operational stresses. Mean that working with the high performance without taking our consideration about the shutdown reasons may be due to different threats, as we will explain in the upcoming slides. This will expose our equipment to forced shutdown or emergency shutdown, and the relationship, this is the too much thinner between working with high or the high performance and the total shutdown. Also, we have some statistical indicate that around 60% from the major incident is related to invisible threats. This is another point need to be attention. This is around approximately 60% from invisible threats have a direct impact for or of major accidents. Okay, let us take an example to explain what will be or what does it mean by this percentage and why this is statistical indicate that the invisible threats. But before going to take an example, let us explain what does it mean by invisible threats. Invisible threats, we can say in another meaning, a small defect. Small defects cannot be captured by traditional ways or traditional techniques, so that it's considered invisible, and unfortunately, finally, it will affect or have a major effect in the major accidents. The most popular example for this corrosion under insulation. So we can see the insulation of the pressure vessel or the piping system in a good appearance, but still have some gaps or some weak points, or we can say some degradation points or damage from the thermal insulation. These areas will affect the underneath or the outside or external surface from the pipe or the pressure vessel or the storage tanks. In case of CUI condition are in place, means the temperature of the CUI achieved, and the operation may be sometimes intermittent surface. So in case of CUI condition are in place, so that we can say this is invisible threads, unless otherwise we should take our attention at the integrity team from this invisible threads. Another example we can see in this photo, external corrosion. However, this shallow external corrosion, but if we are focusing deeply, we can see that some pitting under the external corrosion, this defect sometimes may be smaller than 1 millimeter, but unfortunately, if we couldn't catch it early, okay, it became invisible streets, invisible threads, and it will be propagated until the failure may be occurred. So this is the second example. Here we are talking about the big threads. What does it mean by big threads in the oil and the gas industry? Any damage in the oil and gas industry will be related to one of the three reasons, or one of the three causes. For example, the first threat, big threat, is corrosion. For example, general or localized, sometimes by fluid chemistry and by temperature. So this is the first one. Second one from the big threat is cracking. Means sometimes stress corrosion cracking may be coming from fatigue and brittle fracture. For example, high risk due to no warning failure. No warning failure means that this is suddenly occurred, the brittle fracture. This is the second one. Third one is the mechanical thread. For example, most popular example for erosion, cavitation, and vibration. This is the most common occurred in high velocity piping. So here we are focusing in the big threads, three big threads. We have our reference API recommended practice 571 damage mechanism affecting fixed equipment. There are 67 damage mechanisms based on some of them related to the corrosion, some of them appeared in the cracking or due to cracking, and some of them related to the mechanical action. The key damage for the mechanisms, for example, in the previous slides, here talking about general, and if we are talking about the first threads or big threads, corrosion, and as we explained in the previous slides, is related coming from chemical or electrochemical reaction of the material with its environment, will appear in the localized pitting, often more dangerous than the general thinning. Sometimes, and by the way, it's difficult to catch this localized pitting by traditional techniques. so that the local points or local pitting most damage than the general pitting or general thinning. Here in right side, talking about corrosion under insulation, as we explained in the previous slides, whenever the corrosion under insulation CUI condition is in place, mean that what does it mean by corrosion under insulation condition? Corrosion under insulation condition means temperature range, and this temperature range will differ than from carbon steel, than stainless steel, then duplex. Additionally, the work with the operation or operating regime mean that this operating regime may be continuous or intermittent. If intermittent, so that it will be directly one of the CUI condition. Here also we are talking about stress corrosion cracking. Stress corrosion cracking is a combination of tensile stresses, corrosive environment. Finally, it will lead to fracture or brittle failure. The most common example for this is acoustic media and amine media. Okay, so the residual stresses from the welding itself, and combined with this kind of media, corrosive media, will lead to this cracking. So stress corrosion cracking, we can summarize it in this triangle. For example, this kind of material, and the second angle from this triangle is media, and the third angle is stresses. These stresses, the resources of these stresses is coming from the residual stresses from the welding itself, unless otherwise applying post-welding treatment to remove or to stress relieve these stresses, to break this triangle to avoid occurring stress corrosion cracking. So one of the most popular stress corrosion cracking is related to the caustic media and amine media. Finally, this will be clearly in the weld area and heat affected zone. Okay. Additionally, we are talking about the mechanical dent. Mechanical dent also considered as one of the major threats we should focus on. Sometimes heavy vehicle passing from the over the flow line or the trunk line without any sleeve and without any barrier, and dents will be in place. These dents, unfortunately, pass the acceptance criteria when we apply fitness for surface assessment. We found this dent is more than or exceed than the acceptance criteria, so that we should take immediate action to avoid any cracking from this dent. We have these questions for discussion in our career or in our professional experience. What is or which threat is the most difficult to be managed? Is it hidden CUI in high temperature lines? Is it will be stress corrosion cracking in welds? Is it pitting or in aging piping system? Is it human error during entity reporting. Which mechanism surprised you most? Which reason? Which reason is difficult to be managed from the four ones? For example, is it will be hidden COI in high temperature, keeping in our mind this temperature is still in the range of COI. Okay. Or stress corrosion cracking, as we explained in the previous slides, is especially coming in the welding if the weld is poor or doesn't achieve the high quality or the soundness during the construction or during the repair, meaning that there are some residual stresses, and the heat treatment or stress relief operation or stress relief process doesn't implement it well. So that still we have some stresses inside the weld itself. It will be affected in the operation. Here, the chain started from a small defect initiation, then this damage is still propagated and grows. This is a steady propagation or steady progression. Then the first step from the failure coming later, but there are some signs of failure. For example, loss of integrity, safety margin. For example, this point eroded, and then finally failure or plant accidents. This is a chain that explain and from understanding from the small defects until reaching the failure or plant accident. Defects grow, okay, into major failures. Understanding the mechanism is only in the first step here. So that means that any small defect should be treated well, should be monitored, and take a necessary action. Inspection process or inspection operation. If the inspection it was an effective inspection means that this inspection select a proper NDE, a proper timing, inspection timing or frequency, and skills. This means this is the three parameters of inspection effectiveness. So in case of inspection, applying the inspection well in the effective inspection by these conditions, at that time the inspection will considered as a defense barrier, avoiding or catching the small defects and take the necessary action after that, after doing assessment and take the necessary action, meaning some re-rating or some temporary repairs, or otherwise applying, we are forced to do emergency shutdown to restore the equipment integrity again in safely manner. So early inspection will interrupt failure propagation. Okay, early inspection, and here we should stop at this point. Early inspection means early effective inspection. That's what I want to explain. Effective inspection is not like any inspection, any inspection without addressing the different kind of damage mechanisms, the susceptible areas, and the appearance and the appearance and the inspection procedure finally is poor or weak, so that the inspection at that time will not affect, and we cannot consider one of the barriers. Here, this is engineering integrity path from the damage mechanism, identifying the damage mechanism, then applying the inspection to detect this kind of damage mechanism, then do some assessment by addressing the inspection results, okay, do some engineering fitness for surface evaluation to do to get the final decision if we are going safely or we should take a necessary action immediately. Finally, take the decision. Is it needed to final repair or replace or re-rating? Okay, so this is the engineering integrity path. It started from identifying damage mechanism, then how to detect this kind of damage mechanism, and how can we do some assessment for the inspection results, then what is the best recommended action to keep our equipment in safely mode. Here, this graph also the relationship between the asset condition and the time. We can see from this letter D means design or the original design. From the design until the installation, no any bad effect, no any side effect on the equipment itself. Then working in safely manner until reaching to this point at which failure can begin after certain time from the operation, and exposing to the operating parameters and operating condition, specifically if this equipment work outside the inspection, or outside the integrity operating window. So this is a critical point. Critical point mean that after certain time from installation, okay, and our equipment exposed to different parameters, different variables, operation parameter and operation variables, specifically if these parameters out of integrity operating window, mean that we are in the starting phase for the point of failure. Then reaching to this point, degradation point, until reaching to this location or this point, fatality point. Integrity decision roadmap. For example, we have sub-standards. For example, API 510 for the pressure vessel, API 570 for the piping system, 653 for the storage tanks, 571 for the damage mechanism. Each standard, okay, focus on different points of view. For example, here for the pressure vessel, API 510 focusing on internal and external degradation, and decision may be recalculation or re-rating, or sometimes repair, or sometimes applying repair. Okay, this is for example. This proper integration between the standards and to ensure that zero leak or zero accident plant environment. Okay, so the main objective from this slide is to explain the integration between the standards or inspection and integrity codes and the standard, taking into our consideration also the inspection specification for the client itself. Finally, we have to achieve or ensure zero leak and zero accident plant environment. Let us remember that this percentage that we discussed in the previous slides, when we talk about this statistical percentage, indicated that around 60% of major incident from the small defects, or we can say from hidden or invisible threats that will affect directly the facility equipment. Here, if we want to study or to explain some barriers to avoid any failure, okay, a small defects often first a hole. Okay, so we have some barriers as we can see in this Swiss cheese model. Okay, the first barrier is design margin, and this is, by the way, this is the first barrier, and the most most important barrier is starting from the design margin and design phase all. Okay, so in case of any deviation in the design, so that this equipment will exposed by operation to different kind of damage mechanism, and finally achieving and reach out to failure occurrence. Barrier number 2 is operating procedure. And by the way, operating procedure should be based on, or we can say it should include integrity operating window. Okay, so any operating procedure should consider and should recognize integrity operating window. Why? To avoid any deviation, as we explained in the previous slides. If any of the process parameters exceeding the boundary or get out of this boundary, so that the mechanical structure or equipment structural integrity, it will be affected directly, and finally it may be failed, or we can say a huge failure or incident. Third barrier is inspection and NDT. Okay, inspection and NDT, as we explained also, in effective inspection is considered as one of the defenses or barriers. Okay. Finally, to avoid any failure, we are forced to do shutdown to restore the equipment to its original condition and working safely without any interruption and without any problems. Here, this slide summarizes the stages that from the initiation to rupture. Okay, start from initiation, then this is an occupation, and this after that propagation rapidly, and then leakage. We consider this a warning to the rupture that will be at the end of this chain. Okay, the rupture will be occurred and a catastrophic failure may be in place. Silent killers or silent damage may be due to pitting corrosion or maybe a single pinhole. So we have to focus on the small defects, as we explained many times before. Small defects should not be ignored by no case, but it should be monitored and should be focused on to avoid any propagation and this chain. This corrosion under insulation also. By the way, our slides will have a different type of or different examples. Here also a mechanical fatigue in welders. This is started from the repair or from construction phase. As we can see, this is a red arrow here on the right side. Okay, this is some cracks in the weld itself, and this due to the some vibration of the coming from pump or compressors, maybe some fluctuation occur. So finally, it will be failed, or failure may be cleared. Here is this stress corrosion cracking, as we explained before, susceptible material. This is the triangle that we discussed before, my guys. Especially these susceptible material. One of the first angle and the corrosive media, and then tensile stresses, and we explained also the residual stresses coming from the weld, or applied stresses coming from the internal pressure, or by hoop stresses due to internal pressure. Finally, we can see in our facilities some of stress corrosion cracking. In the form of cracking, this cracking may be branched, maybe finally reach to a huge or catastrophic failure. This is another example for internal erosion and thinning. Erosion coming from solid particles and high speed or velocity, especially in the elbow and T joints. Okay, and this area is susceptible to be some knocking by solid particles. Then it could be eroded. Then the corrosion started. So corrosion may be in place, and this is considered as one of major threats. Also, finally, it will also affect the piping system, and maybe reach out until get catastrophic failure or leakage, depend on the media, and depend on the hydrocarbon surface. This is an example for case study: maintenance cost, downtime cost, or downtime, and then safety impact, and this total cost. Here, this table explains the relationship or comparison between early repair and plant failure. So if we have small defects from the beginning, and this is small defect unfortunately ignored. Okay, so we can see in the maintenance cost here, the number or the value is too much high for a spool replacing, otherwise from some local wrapping or sleeve. For example, let us give an example for this. Suppose if we have a pipeline, this pipeline passing from under the road cross, okay, or there are some ramps for vehicle moving, okay, and the pipeline without any wrapping, and the pipeline without any sleeve. So this pipeline will be exposed to external corrosion from the soil itself, and also may be affected by vehicle transportation of vehicle moving, especially heavy vehicle, and without sleeve over the pipeline. Finally, we can see the difference between the early repair or mitigation action, which could be applied to avoid plant or the failure itself. Firstly, here 0 hours. Here take emergency repair around 336 hours, stopping to repair or to cut and replace this spool. Safety impact, nothing here, under control, this activity, but here extremely. And sometimes this failure may be if this is gas pipeline or oil pipeline. So unfortunately, it could leakage maybe appear in the form of fire, or sometimes injury for the people. Here, total cost, we can see the measure. So what I want to say here, this slide summarize early repair or early mitigation action could be applied to avoid especially for small defects, or small defects could affect and invisible threats until failure may be occurred. This acceleration may be due to some process condition, for example, high temperature, pressure, chemistry, as we explained many times before. Here, this is NDT also. NDT is considered as one of the major player or important player in the inspection effectiveness, as we discussed before. So let us remember that when I said that inspection effectiveness is depend on the inspection, the damage mechanism form and susceptible area, and the skills of operators or NDT examiners, and also the inspection procedure itself. So in order to achieve an effective inspection, we have to focus on the NDT detection as detection barriers. Here, talking about the risk-based inspection strategy, we are also going to talk about some of RBI, risk-based inspection, focusing on critical points. This or too much high. This is a high risk. This is a medium risk, and this is a low risk. And distribute the effort and for inspection based on the risk, based on the risk. Okay. And after that, we can focus on the high risk equipment or high risk parts from the equipment itself. Here, the rule of thumb, human competency, means safe plants are not run by luck, by the way. They are run by professionals who respect the warning potential of every small defect found. This is one of the asset integrity principles, and we have to focus on and take in our consideration in order to achieve the integrity of our plants, our facilities. We have to be a professional and respect warning. And here, specifically talking about, please don't ignore any small defects. Okay. This is a inspection life cycle, and the inspection responsibility. We are going to talk about risk-prone areas, using the historical data to predict failure. We have plant, oil and gas plant, from some equipment. Okay, and what is the most or highest risk area? Okay, highest risk area. So we should identify the highest risk area here or here. Then this is high risk area by the facility. Then deeply going on this area, applying some approaches to identify the high risk location and the high risk equipment in this area. Okay, let us see what will be in this discussion. Firstly, we should know the criteria what make an area high risk. What is the reason? On which basis, in which basis that we classify this area as much higher risk than the other areas? In which reason? We have some parameters or some criteria. These criteria will be applied then to identify is it which area is considered high risk, which area is medium risk, which area is low risk. For example, stress concentration, severe operation, stagnation zone, poor drainage and fabrication flows or defects. Okay, stress concentration, for example, geometry change like nozzles and sharp transitions. So if it in our place, so that it will be directly high risk area. What else? Severe operation means high temperature, pressure cycles, or rapid cooling. Okay, this also will classify or achieving that our facility or this equipment, if exposed to severe operation, it will be a high risk equipment. Stagnation zone, for example, dead leg and some piping portion, or some nozzles, for example, and poor drainage, so that trapped the water and the moisture, causing corrosion under insulation. Also, fabrication flow means some weld defects, especially in heat affected zone, are metallurgical weaker. Okay, so in order to summarize the risk formula: damage mechanism plus stress level plus operational environment. This is the criteria or the parameter. How can we classify any area? If it will be high risk or medium risk or low risk. In the pressure vessel, we are talking deeply about the pressure vessels and some piping, and also for the storage tanks. For the pressure vessels, the critical location, we can see nozzles and well seam and bottom head and support skirt. High stresses points are often side fatigue cracking. Weld seam also, like for example T joints, where longitudinal and circumferential weld meet together, is considered as a high risk points in the pressure vessel. Bottom head also, sometimes some of hard deposits or sediment accumulation lead to localized pitting and microbiological corrosion, and the corrosion under insulation became an approach. Okay, support or skirts, thermal expansion stresses, and also corrosion under insulation, the vessel to support interface. Okay, for the pressure vessel, okay, location bottom nozzles, water stagnation due to, this is the reason, due to water stagnation, then the form of damage will be pitting, then finally result in leakage. This is the sequence. Okay, in the pressure vessel, especially in the bottom nozzle. Okay, water stagnation may be in place, then the damage will be in pitting mode, and then finally result leakage. For example, if we have a nozzle, this nozzle during turnarounds, 2-inch drain nozzles on the separator was found around 80% wall loss. So the main reason at that time to identify heavy brine settling is stagnation or stagnant condition at this nozzle neck. This is the risk due to or bad performance from the bad performance from the operation team. There are no any flashing on time, and that which lead to stagnation, and then finally lead to pitting and leak. Here for storage tanks. For storage tanks, the most dangerous or critical area is annular ring, also shell to floor or to shell to bottom weld, roof support, and bottom plate, where water accumulation lead to microbiologically induced corrosion. Okay, annular ring, this is high stresses, especially the critical zone. Okay, critical zone means 3-inch radially. If we have inside this, suppose this is the tank bottom, and we can 3-inch radially from the shell itself. Suppose here the shell, and this area of the critical zone, which consider as a part from annular ring. In case of the tank with annular ring, this area is too much critical location, and have focus on this area and give special attention. Why? Because the tank stresses or shell stresses on this location. This the failure path in the tank's water entry, concentration, then finally failure. This is another scenario for practical failure path in the storage tanks. For example, if water entry moisture enters through the damaged shell to concrete cells, mean corrosion underneath bottom. Here, suppose if we have the tank, this tank, for example, from this location, there are some gaps, and then the water will be enter from here, achieving finally corrosion from the soil side. Okay. Concentration, oxygen concentration cell from under the floor plate here due to aeration, and then finally localize the thinning lead to product spillage into the soil. This is another scenario for the tank. Corrosion. Okay. This for piping system, common failure spots. We can see dead-leg, injection points, elbows, and COI areas. These areas is considered as the most common failure spots in the piping system, as we explained. Sorry. Here, this invisible thread COI for corrosion under insulation, and this point is critical, as we explained many times before. Here also for the pipeline. So we discussed some scenarios related to the piping system and pressure vessels and the most common susceptible areas in the storage tanks. And now we are talking about pipeline external and mechanical risks. So we have some areas need to be focused on and give our attention. For example, grit welds in the pipeline and road or river crossing, coating holidays, mechanical dents if in place. Okay, this is the points also need to be considered in the pipeline. This is the most damage or most high risk areas may be occurred damage at any bit from the pipeline. Here, to summarize the importance of inspection, the inspection should be predictable. Be predictable and should focus efforts, okay, and then finally applying some of the root cause analysis or investigation. Okay, so the inspection logic should be predictable, means failures are not randomly happens, but it should have some logic says. And then we have to focus our effort, for example, in the area and time. Focus effort means time and location and the high risk equipment, as we discussed before. This which will be comes from RBI plan. So the main output of RBI is to get an inspection plan. This inspection plan based on the risk calculation and the risk assessment, and focus on high risk equipment other than low risk equipment. Okay. Finally, in order to get inspection logic, we should apply some of the investigation and ask some questions to get the main cause or to avoid in the future. Our message or my message to the inspectors: don't just inspect the easy spots, okay, but you have to do your best, climb and look under the insulation where the risk hides, okay. And this is a message to you as an inspector, and this message to be passed through, from time to time, and also it will be considered by the way in the inspection plan for each equipment. If we are going to talk about the damage mechanisms, we discussed previously some major threats. Catastrophic failure may be due to internal pitting, may due to mechanical dents, may due to soil side corrosion, as we discussed in the tanks, okay, soil side corrosion, and also corrosion under deposits when we are talking about dead leg. So there are some stagnation, finally deposits inside the pipeline, as we can see. This could affect the pipe itself, and then corrosion under deposits will be appear. So in order to control it, we have to apply a routine bigging program to avoid this accumulation, and also avoid any stagnation by periodical flushing in suitable frequencies. Okay. Here talking specifically about dent and dent stress cracking. This slide summarize if we have some dent in the pipeline, for example, or we can see this dent, okay, should be addressed well, as we can see here in this slide, in this photos, this finite elements and this fitness for service assessment level 3 to identify as it will be passed safely for a specific time or need an immediate action or an immediate repair recommendation. Okay. Here also external soil corrosion. Apply CIS and direct current voltage gradient surveys to avoid any propagation of any external corrosion could be appeared. We have in this photo some pipeline. This pipeline, underground pipeline. This underground pipeline should be coated or should be wrapped well, and should be monitored from time to time to achieve the cathodic protection coverage. CB system should be checked periodically to achieve its functionality, to keep the outside or the external surface from the pipe without any external corrosion. Here also some barriers, protective barriers for the pipeline. This some butai. One of the process safety investigation, and also this is some mitigated actions. And now we're going to talk about the why damage mechanism drive inspection. Why damage mechanism drive inspection. Okay. Damage mechanism, as we discussed before, damage mechanism should be addressed by corrosion engineer. Then the corrosion engineer will highlight the most susceptible location and which kind of damage could be appeared. And finally, the inspection effectiveness realize understanding the driver of the degradation, as we discussed many times in the previous slides. Early effective inspection will be considered as one of the most defense player or mitigation action for the failures. also some damage mechanisms, and we are going to talk about corrosion and inspection. This also discussed before. We are talking about asset integrity management. Asset integrity management. Due to the time, so we will jump for to reach the third item with us or outline. Okay. Implementation of international standard and API code. For example, why asset integrity management? Asset integrity management. So the also to be in place, and reliability, finally achieving the life cycle based on system ensuring safety, reliability, and sustainability of critical and physical assets. This is the main objective from the asset integrity management, is to minimize the risk and optimize the maintenance costs and extend asset lifetime, and keep the assets in the same condition, or the good condition and safely condition during the lifetime. This the strategic of big picture. Okay, we can see here, start from the design. So in order to achieve the best way to achieve the or to manage the assets during lifetime, is to start with the design phase. So if the design phase have been applied and in professionality and reviewed well, and nothing, everything is in place, no any deviation from the codes and standard and best recommended practice, and the design already reviewed well, then moving to construction phase. Construction phase also should be followed and supervised well to achieve the best optimum soundness of the construction phases, and then passing or hand over the equipment to the operation team. The operation team should also working inside the integrity operating window, as we discussed before, through establishing operation manuals and then decommissioning for at the end of the lifetime. And the integrated life cycle flow for the asset integrity. Okay, started by leadership, then governance, then design phase, as we discussed, then damage and then inspection. Damage mean damage mechanism and some inspections, and then maintenance, and then achieving or minimizing risk, and then finally to get a data, and then people here mean the competency of the team who are involved in the life cycle of the integrity asset integrity management. So in case for foundation pillars from 1 to 3, this foundation pillars, this technical core, until here, this foundation pillar, okay, here this technical core, and this the rest ones we will discuss in details. Leadership, active commitment and resource allocation with to prioritize safety over the production targets. This is the leadership, and by the way, this is the most, or we can see this is the first pillar in the asset integrity management. First pillar. clear policies, standard, and performance metrics that define the rules of engagement. Then the design phase to ensure assets built-in serviceability and accessibility. So the establishing the base or the foundation of the asset integrity by leadership who have the power and the commitments. Okay, then applying standards and the reference, then design phase. Technical core is from pillar number 4 to 6. For example, corrosion and damage should be addressed well in asset integrity. So degradation management, here establishing the base of asset integrity. Here degradation management started from pillar number 4, 5, and 6, means from corrosion and the damage for different reasons, as we can see, H2S corrosion, CO2 sour surface or fatigue, or regardless the kind of damage. Okay, pillar number 5, inspection assessment, using and utilizing entity and visual methods to quantify degradation. Pillar number 6, repair and mitigation actions, executing corrective actions to restore technical integrity. So the sequence is for degradation management is to identify damage and by detect it, and then take a proper action. Pillar number 7 until number 9, this is a complementary integrated pillars in the asset integrity management and related to fitness for service assessment and risk-based inspection and the management of a change. Okay, management of a change. Okay, this is the rest pillars, but we are talking about specifically in the organizational analysis, data and people. Okay, to achieve system sustainability, integrated data plus competent people. The role of inspection in asset integrity is to identify the threat and the corrosion defects, then avoid the consequences of failure or leak. Inspection transform uncertainty into data and act as a risk barrier. But here we should remember that to get the best objective from inspection in asset integrity, it should be effective inspection as we discussed previously. The operational backbone is the NDT team and decision support. Inspection management itself. Here talking about inspection management. Inspection management is the operational engine that connect the technical damage mechanism or knowledge to high level of risk decision. So in order to achieve the optimum from the inspection, we have to apply an effective inspection, meaning that started by inspection management. Here also beyond the NDT means structural cycle involving planning and prioritizing and reporting. NDT here is also as one of the sub barriers, or we can say included in the inspection management cycle in the asset integrity. Why? Because NDT examiner should take special awareness from time to time. Why? Because they are playing an important role to getting the the inspection results or output from the inspection. They should know that they are working or they playing an important role in the asset integrity rules. So, an asset integrity, applying an effective inspection through or via competent people or competent entity team will be clearly sufficient to achieve the operational backbone in the asset integrity. Here, some of the RBIs of inspection focusing in the piping system and pressure vessels also, until from the starting from installation and the current data and the retirement team minimum required thickness. Mean that this slide explains the corrosion rate determining lifetime. This based on this is by integrity team. Okay. For example, for RBI, we should take some examples in our MOVE RBI system. Risk-based inspection. We will close our session by risk-based inspection and identify which and what is the main reason for RBI. Risk-based inspection. This is an approach to be applied to focus the inspection efforts and over the high risk area, as we can see in our slides here. This is the risk matrix, the relationship between probability of failure and the consequences of failure. Okay, and then to prioritize the resources for maximum safety asset integrity. What is a risk-based inspection? What is a risk-based inspection? Risk-based inspection, as we say, that this considered as approach focus inspection efforts where they are needed to most balancing the frequency and time of inspection against the risk profile. So this is a systematic life decision making process. In order to calculate risk, okay, we should calculate or assess the probability of failure and then consequences of failure. What does it mean by probability of failure? Probability of failure means the susceptibility of damage occurrence. Consequences of failure means the sequence of the if the leaks occurred or the some rupture happened or whatever. Okay, what is the consequences? By the way, it will be negative impact. Will be addressed on the human and the environment and the production interruption. Factor driving the probability of failure: corrosion and erosion, thermal stresses, and metallurgical issues. All of these affect the probability of failure. Okay, factor affecting or categories of consequences, as we discussed. This will be addressed: safety and health, environment, and economical impact, being production losses and interruption. Okay, this is we have this equation. In order to calculate the risk of any equipment, we have to calculate the or assess the probability of failure and the consequences of failure, and finally we get the risk and do some sequence to do some risk management and risk assessment, and finally to get the inspection plan, focusing the inspection efforts over the high risk location. Take an example for high risk and medium risk and short risk. This will be explained and expressed in this risk matrix. For example, 5 by 5. This is a relationship between the probability of failure and the consequences of failure. And this area is high or too much high area. This area is green area is low, and this area in between even high or moderate risk. RBI screening tools is considered an important tool in the inspection or as integrity overall to apply some screening. Which equipment will be high risk, which equipment will be low risk and medium and high risk. Okay, a standard framework in order to get this study. In order to get this study from ABI 580 and ABI 581, this recommended practice or recommended practice. Let us take the difference between both. ABI 580 recommended practice. This is recommended practice qualitative, okay, but for 581 quantitative methodology means specifically it details steps to calculate and the risk and the in details. Scoping here and the ABI 580 guideline for establishing program, a specific formula here and the calculation. High adaptable, low perspective in oil and the gas. Here outcome from ABI 580 is risk ranking, but here is financial and the area of risk metrics. Okay, so this is the main difference between ABI recommended practice 580 and ABI 581, but both are working together to manage the risk and to establish or generate inspection plan. Here, this implementation of working flow is screening, start by screening, then assessing, gathering data to calculate the probability of failure and consequences of failure, then applying risk ranking, then applying some defining the planning or inspection plan here. And then finally to update the inspection plan by reviewing the findings. Let us take a case study. Refinery heat exchanger equipment. Our equipment is crude unit preheat exchanger. The material is carbon steel shell, stainless steel, the tube material. The condition is high chloride content detected in crude. The standard fixed 3 years inspection cycle. This is the inspection frequency. And now we are going to apply the risk-based inspection to achieve or to see how can RBI working. Okay. For each part, risk mapping analysis started by shell side analysis at the calculated risk based on the probability of failure and the consequence of failure is found is low. And for tube bundle is the risk calculated is high. Here they reduce the interval into from 3 years to 1.5 years. Okay. traditional view, inspect everything every 3 years. This will insufficient, inefficient for shell. Okay, risky for the tube. RBI view, finally, shift focus on high risk tubes. Defer low than, better than wasting time, wasting money, and wasting effort for low risk shell inspection. So this case study, okay, here also we can see that traditional costs is too much high. Then applying risk-based inspection, RBI, it became approximately half. Safety confidence is reaching around 100%, is achieving specifically 95%. So results is half of the cost reduction, or 50% percentage cost reduction, will increasing detection and probability of the tube leak by 30%. The future of the integrity digital RBI, digital towns, and machine learning and reporting inspection. This is the upcoming. And by the way, here also we can say AI will be included. The power of RBI is to achieve to prioritize the inspection, okay, on the high risk. This is the main objective of RBI. Now, from my side, I finished my session, and welcome with any question and related to the 4 subjects that we discussed in our session. Dr. Ahmed, now I finished, and I'm hearing to any welcome with any question from our guys who attend.
Okay, gentlemen, any question? Okay, hence there is no question. We would like to thank you for your great and useful session, and thanks for everyone for attending this participating. Inshallah, see you in next session. يعطيكم العافية. شكرا.
See you later. Assalamu alaikum.
Thank you, sir.